We found s squared to be equal to 23.804 for the data used to predict the average weight for supermodels given their height. Find s and then state the largest deviation we would expect between any of the actual data points and our least squares line. Okay, so finding s is a really simple matter in this problem because we're given s squared, so all we have to do is take the square root of s squared and we will get s. So since s squared is equal to 23.804, we can show that s is equal to the square root of 23.804. All right, let's see what that turns out to be in our calculator. So we end up having the square root of 23.804, close up the parenthesis, and we get the answer 4.879, let's say. Okay. Now, once we have that, I want to calculate a value 2s, 2 times s. So I'm going to do times 2 to figure out what 2 times s is in this problem. That's 9.758 if you do twice s. We'll talk about why we want to know this in the very next step of the problem, which is where we want to state the largest deviation we'd expect between any of the actual data points and the least squares line. That's our answer, actually, to that question. We would expect that the largest deviation between any of the actual data points and our least squares line is 9.758. That's the biggest value we'd expect to see. The reason why is we have this kind of classic statement that we use to interpret s. So here it is. The classic statement says that we expect approximately 95% of the observed y values, that is the actual y values, to lie within 2 standard deviations of their respective least squares predicted y values. That's the y hat values, right? So basically what we're saying is that if we actually take this difference, y minus y hat, these differences, the absolute value of them will be less than 9.758, approximately 95% of the time, right? And what we mean by that is very simple. Well, let's first of all talk about where the 95% comes from. Back in Stats 1, you would have learned a rule called the empirical rule, and we learned then that approximately 95% of the observations lie within 2 standard deviations from their mean. Well, the mean for the error term in a least squares prediction model is 0. So what we're saying then is that essentially surrounding that mean of 0, if we put 2 standard deviations surrounding the mean, we'll capture 95% of the observations because the error term is also assumed to be distributed as a bell-shaped distribution where its variance is approximated by this s squared value we just came up with, and its standard deviation is approximated by the s value we just came up with. So in that case, what we're basically saying is that, again, the difference between what you think the actual value will be versus what it really is in reality, that those differences should be within twice the standard deviation. So in this problem, we expect that these error terms are generally, the absolute value of the error terms is generally something less than 9.7. So it basically gives us an idea of how far we'll miss the mark. Say in this problem, we're talking about supermodels' heights and weights. Let's say we made a prediction for one supermodel who is 6'1", we said that she should be 120 pounds at that height. Let's just say that we did that. I'm not saying that that's correct, but let's say we came up with that prediction. And we observed an actual supermodel to be, say, 125. Well, the difference there would be 5, and of course that difference is in fact less than the 9.758. So it would be one of the observations that falls in this 95% of all the observations that will lie within 2 standard deviations from our predicted value, right? So in other words, only 5% of the time will we miss the mark by a value that's greater than, or in other words, only 5% of the time will this difference ever be greater than 9.758. So that's kind of helpful. It gives us an idea of, how bad we'll mess things up basically when we do mess up, right? On average, the error is 0. So on average, we get the prediction right on average, but that's on average. Of course, for a particular observation and prediction, of course, we're going to have error. And this gives us basically kind of a bound, right? A set of boundaries, right? Basically. So we don't expect to underpredict or overpredict by more than like 9.758 very often. In fact, only about 5% of the time will we mispredict by something larger than this. Okay, so that's the interpretation of S. And to answer this last question, you know, as I said before, when it says state the largest deviation we would expect between any of the actual data points in our least squares line, that answer is simply 2 times s.